last class we were discussing about the idea of doing away with the PMOS stacks entirely, right? And therefore we came up with this idea of a ratioed circuit, right? Or pseudo NMOS logic. Okay, and the basic idea was very simple. You have a pull down network which is only NMOS transistors to ground. The PMOS transistors you replace by a permanently on PMOS transistor. Going to be connected to ground, which means that this PMOS transistor is always on, and the idea behind doing this is the input is not driving my PMOS transistor. Because the PMOS transistor by nature has to be double the size of the NMOS to get the same current, the PMOS transistor was a guy who was killing the logical effort, was making the logical effort very high, especially for NOR kind of gates where the stack is now going to grow on the PMOS side rather than the NMOS. So the point is, we had to do something in order to reduce that logical effort. So we said remove that PMOS, don't allow the input to drive that PMOS transistor. So the capacitance that the input sees is only because of the NMOS transistors on the pull down network, right? And of course, if you take now a pseudo NMOS inverter, which is like this, this is my output Y, then the issue is, if you take the case when A is 1 or A is 0, then there is no problem, because the output will be VDD, the NMOS transistor is going to be off. Only the PMOS will be on, there is no current from VDD to ground, right, other than leakage current, and hence there is no issue when we are talking about the output going to a logic high. However, if you now try to turn this input on by instantaneously taking my input from 0 to 1, then what happens is you are now going to have a fight between the PMOS transistor which is trying to pull the output to VDD and the NMOS transistor which is trying to pull the output to ground, right? And therefore the output now will go and land up at a logic VOL, output logic low, which is greater than 0, right? And we did some calculations and we figured that VOL is simply proportional to WP by WN, where WN and WP are the widths of the NMOS and PMOS transistors respectively. If you make the PMOS transistor stronger, that means it is going to pull the output high with more current, and therefore it is going to take the output closer to VDD. So you have to keep this ratio appropriate so that the output logic VOL is low enough. Remember that when I cascade this gate to another inverter, let's say, right, if I want to cascade this to another inverter like this, in order for this circuit to work correctly, VOL should be less than VIL of the next inverter. Only then it will get recognized as a logic low. So there is a constraint that we have to keep it low, and we have to keep it as low as possible. So the way we do it is, I'll give you a specification saying the VOL has to be lesser than this value, like say 0.1 volt or something like that. And then you find out what my WP by WN should be. Okay. And therefore I will say that depending on the spec, let WP by WN equal to alpha. Is WP by WN, that is alpha, is it greater than 1 or lesser than 1? I'll ask you again. What should VOL be? Very close to ground, maybe 0.1 volt. So WP by WN has to be less than 1 now. That's the difference between the static CMOS logic and the pseudo NMOS logic. There is, the PMOS is now, we are sacrificing the pull-up strength, of course, in the process. But for the logic to work properly, which is of primary importance, you can do timing and other things later. First, the logic has to work correctly. The PMOS has to be weak, which means that WP by WN will be a number which is less than 1. Alpha is less than 1. Right? It can be maybe slightly greater than 1, but most of the time it will be less than 1. Okay? So now with this, first thing we will do is to construct our unit inverter. Okay, we did this in all the cases, even in the high skew logic, low skew logic, we said we will construct our unit inverter. Okay, so let's look at the construction of a unit inverter first. Because if you understand this, then the logical effort calculation becomes very simple. So let me take a static CMOS. Okay, let's go back to how we constructed our unit gates. I had a capacitance, load capacitance, and I said this has to be 1 and 2. Right? Now when I constructed this is my unit inverter. When I constructed my NAND, it was like this. Right? We said this has to be 2, 2, 2 and 2. So why did we say 2, 2? So that the effective resistance is still R. Right? We said this also will give me a resistance of R both ways. Right? Even this will be R. Okay. So we were able to combine series transistors in order to find the equivalent resistance, and we match the resistance in order to construct our unit gate. This gate can be sized up, you will get more drive strength. Similarly, the inverter can be sized up, you will get more drive strength there as well. Right? But the unit inverter is the pull up and pull down, right? Pull up / down resistance equal to R. And what is R? It's basically the resistance offered by a unit NMOS transistor. Right? The 3 VDD by 4 ID. Now the problem is, can I apply the same logic to my pseudo NMOS logic? Let's look at it. I'm going to ground this guy. This is VDD A, and this is my output that's driving a load capacitance. We only know one thing, that WP by WN should be alpha. Right? But WN can be anything, and WP will scale accordingly. So therefore, I am going to say let WN equal to beta, which implies WP should be how much? Alpha times this is beta, and therefore this is alpha beta. So now my question is the following: should the unit pseudo NMOS inverter have beta equal to 1? What happens if my beta equal to 1? The NMOS transistor is the same, right? That's what we have been doing. If you look at all the cases, this 1 has been basically, scaled so that you get the equivalent resistance there. Can I do the same here? Beta equal to 1. Is it possible? The catch here is, unfortunately, my PMOS transistor is also conducting when the output is being pulled low. Okay, here, by the way, inherently we are sort of saying, okay, I am going to pull down the logic very quickly. So we are sacrificing the pull-up speed because we have to lower the PMOS size. We have no other go so that the low logic works correctly. So in some sense, I have already compromised the pull-up speed. That's already been done. So I'm not going to worry about what the pull-up speed is. What about the pull-down speed? That's what I'm going to worry about. So in the pull-down case, I have some current which is coming from my PMOS transistor always. Right? So if my input instantaneously went from 0 to 1, then there is a current IP coming from the PMOS transistor. There is a current which is going to flow to the NMOS transistor, IN. What is going to be available to discharge the load capacitor? IN minus IP. So I have to look at what this current is. Clearly, IN equal to IP plus IN. So there is a fake current which is coming from the PMOS transistor which is going through the NMOS as well. But that is not serving the purpose of discharging my load capacitor. Why was it okay earlier? Why were we able to talk about resistances and get away? Because if my input went instantaneously from 0 to 1, it turned out that the PMOS was cut off immediately, assuming instantaneous rise. It's only the NMOS that was on, and whatever current went through the load or came from the load went into the NMOS transistor. So we had the condition that IL was equal to IN or IL equal to IP, at least mod. Let me not worry about that sign. All the current that was available from the transistor was used to discharge the load, and ultimately that's what dominates delay. Not dominates, determines delay. Right? You remember we derived the expression for the delay as basically 3 by 4 VDD by I naught by I into what? 0.693. This was R into C. Right? We got some number. Then we said that this is also equal to C delta V by I. Now you have to look at this definition more carefully, because the current that is available to discharge the load capacitor is of key concern to us, not the resistance of the transistor. Okay. So what is it that should be equal to I in this equation here? For my unit gate, we always said that IN or IP should be equal to I, and that's how we calculated it. Even now, it's a load current that we are going to say should be equal to I. This has to be I, and of course I is basically the current through this transistor, the unit NMOS transistor. So can you now tell me what is IN in terms of beta and I? The width is beta. If the unit transistor has a current I, what is the current through the scale transistor? Beta times I. What about IP? Alpha beta I by PMOS current gets scaled by mobility always. Cannot forget this. See, if I have this gives me I, then a PMOS transistor with the same width will give me I by 2, because mobility is half. Okay, so IP is alpha beta by 2 into I. Okay, now I want to substitute this in my equation. I'll say alpha I equals alpha beta I by 2 plus IL has to be equal to I, because that's my unit inverter. pseudo NMOS inverter. So what is beta equal to? Can you calculate? I will obviously go, and therefore I get, yeah, sorry, 2 alpha by, okay, 2 alpha minus, wait, let's just work this out, right? I want to find out beta, right? Oh, sorry, this should be beta times I. Yeah, now makes sense. Thank you. Beta into 1 minus alpha by 2 equals 1. Therefore, beta equals 1 by 1 minus alpha by 2. Right? So now let's take a concrete example. Let's say I want alpha to be half. It turns out that the noise, VOL is low enough if WP by WN is half. This is just one example. Okay. Implies what should beta be? Yeah? Exactly. So this will be 4 by 3. So what is my unit inverter? This is 4 by 3. PMOS should be 2 by 3 because alpha is half. 2 by 3. Okay.